Hello, welcome to the video PS37. We're going to do Coulomb's Law and Electric Field problem set number 2. And again, I'm going to have the timing for each problems in the description. So that's there if you need that. Anyway, so we're going to jump right in with number 1. So here's the problem. In one of his experiments, Millikan observed that the following charges, among others, appear at different times in a single drop. List some charges. What is the value of the elementary charge that we can deduce from this data? So first, I want to point out 3 things. 1. What did Millikan do? So Millikan is famous for calculating the charge of an electron, or the elementary charge, as it seems. So that's what we are trying to solve based on his data he's giving us. 2. The elementary charge we find should be equal to or very close to the elementary charge that we know. Elementary charge E, it is equal to 1.6 times 10 to the minus 19. So yeah, it should be close to. And as you can see, mine's decently close, but it's not exactly close. So how do you get this from the data? Well, here's the thing. We know from this formula, one sec. All right, there you go. We know from the formula in the textbook and that the charge of anything is equal to the number of protons minus the number of electrons times the whole times the fundamental charge. So what does this mean? This means that this E is in fact this charge is in fact a multiple of this E, because this is going to be an integer value, and because you can't have an odd number of protons or electrons, and then E is some value E, and so Q is always going to be a multiple of E. So what does this mean for the problem? That means that all these things, all these numbers they give us, are multiples of E. So what does that mean? That means this guy right here could be E times 5. We don't know, because it depends on what this E is. This guy can be E times 7. So how do we find E? Well, we take the differences between these two, and the smallest difference is going to be E. Because like, if this is 5E and this is 6E, then 6E minus 5E is going to be E, just E. But we don't know if this is 6E or this is 5E. We take the differences between all of these, and we find the smallest differences, that's going to be E. For me, it happens to be between, I believe, 8 and 6. 8, yeah, these two right here, these top two. I think it happens to get me the answer. So if you subtract these two, you get this. And also, something interesting is that if you subtract 11.5 and these two, if you subtract this from this, you get 3.296 times 10 to the minus 19, which is a multiple of this. So as you can see, this guy was 2 E's off of this guy. 2 E's off. So when you subtracted them, you got 2E. So that's how you do the first problem. Second problem. 8 charged particles form a square array. Charge Q plus E. Distance 3.5 centimeters. What is the magnitude and the direction of the field from the center? So I'm gonna copy this so we can work with an image. And let's go to Paint, and here we go. We have this. Right off the bat, let me draw a little dot right in the center. This is our center of the electric field. So there are so many charges affecting it, and if we had to draw a raw body diagram, free body diagram, we'd be out of sorts because there's just so much things which are just going on. So let's make the problem simple for each other by noticing that this is equal to this, this is equal to this, this is equal to this. And the reason why these charges are valuable is because they are equal in magnitude and they are opposite. So let's say the 5Q minus 5Q is on this side, then they wouldn't be opposite. But the fact that they are opposite and equal means that they can cancel regardless of their direction, regardless of magnitude, because they're gonna either point towards or away from the center, depending on the charge, towards or away. And if you break down their components, it's always going to be equal because of equal magnitude, and they're going to be in the opposite direction, so their charges are going to cancel. This guy cancels with this guy. This guy cancels with this guy. This guy cancels with this guy. I mean, it makes intuitional sense. Now, but the only things which do not cancel, this guy and this guy. Alright, so from this point on, we have the center here. We have minus 2q, and we have plus q. So now, we want to know the direction, we want to know the magnitude. So, what we can do is that there's two ways to look at this problem. One is in a positive charge way, and one is in a negative test charge way. We're going to do the positive test charge way. They both yield the same results, but for one of them, you just have to put a minus sign in front of them and flip everything. So, it's not what we want to do. So, we're going to do positive charge. Positive test charge. So, this is positive, this is positive. Likes repel. Likes repel, opposites attract. So we want to know the force on this guy relative to this guy. So because they're both like, this guy's going to try to get away from him. He's not going to go this way. He's going to go this way. Now, opposites attract. This is negative, this is positive. He's not going to go away from him. He's going to come towards him. Opposites attract. So as you can see, the net charge is in this direction. This is the net direction. And this actually answers part B of the problem. What is the direction counterclockwise? This is the right thing they're talking about, and it's exactly 0 degrees. Maybe if your charge is minus E, then it might be the other way, depending on the problem. But that's something to keep in mind. Anyway, now that we have the direction, we don't even actually need to worry about this minus sign, because we just want to know the magnitude. The total magnitude in this direction is 3q. So now, let's find the electric field. The electric field formula is E equals F over Q. But it's also E. If there is no explicit charge, then E is equal to K net charge, net Q, all over the radius squared. So we have this formula. We have D. We know K. We've always known K. I'll just look it up for you. K, constant. Coulomb's constant, and that is, where is it? 8.99 times 10 to the 9th newtons meters squared Coulomb squared. So we have that times K net and equals 3Q. 3Q equals 3E, because in the problem it says plus E, and we know what E is, because E charge, probably find it, yeah. Anyway, elementary charge, we know from problem 1, is 1.6 times 10 to the minus 19. So, we have this formula. We can plug in the things. 8.99 times 10 to the 9th Newton meters per Coulomb to the minus 2, I think. Coulomb to the minus, Coulomb squared. Yep, to the minus 2. So, do you want me to write it out? Here, I'll just write it out. 0.99 times 10 to the 9th Newton squared times, so let's see what it is. Let's go. 3E, so 3 times E, 1.6 times 10 raised to the minus 19 coulombs, all over 0.0, how many was it? 3.5, 3.5 meters squared. Now, this will get you this answer, probably, very, very likely. I would be surprised if it didn't. These cancel, this cancels, you get newtons per coulomb. So the units check out, and so does the answer, most likely. Oh yeah, you didn't see that, because I was just canceling units on the side. I forgot to switch tabs. Anyway, so, let's go on to problem 3. Two concentric rings of radius r and r prime equals 3.2 r, lie on the same plane. Point P lies d away, small ring, uniform charge of Q, and what needs to be the uniform charge of the larger ring so that the net electric field is 0. So here's how you do this problem. Let me delete this really quickly. Delete it. Okay. So let me get this photo. don't know how that happened, honestly. Alright, right here. So, this, I had to look up a special formula for this problem. And the reason, and I'm not going to explain to you how to derive the formula, mainly because I don't know myself, and also because it requires calculus. But the reason why we can't just do some simple stuff is because when you're trying to find the electric field on this point from this guy, you have to factor in what's going on from here, 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 what's going on all throughout. And it's uniform. So there's just so much stuff that you have to, oh wow, you have to factor in that it just doesn't work out nicely. But what does work out nicely is the fact that we have this equation. E1 plus E2 dot 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 E, let's put these vector hats on so we don't get minus like 13 bis, plus E to the n is equal to the net E net. And it tells us that they want E net to be 0, so we can just replace this with a 0. 0. So, and there's also only 2 electric fields, so we don't even need those. So E1 plus E2 equals 0. And actually, they're also in the same direction, so that works out. But here's the question. Here's the thing I had to look up. What is the electric field on an axis of a charged ring? Well, that answer is E is equal to, here, let me do it on this. E equals KQD over D squared, that looks like a B, undo, D squared plus R squared raised to the 3 over 2. So this is just a formula that you have to use for this problem. I don't particularly know why we have to use it, but we have to. So anyway, as you can see, if you want this to be 0, then E1 has to equal negative E2. So if you plug this equation into here, and you like put this in for this, you will get, let me do it here, clear this, you get, on the right side, you get E1, and let's make E1 the inner circle with uniform charge plus Q. It's going to be the inner circle. Okay. Okay. Q, because it says Q is the charge, plus Q. D over D, that's, we'll pretend that's a D. Plus R squared, all raised to the 3 over 2. And by the way, this R is this R right here, because this is small. We're talking about the inner one, alright? This equals negative K, wow, K, and Qn. We don't know this. This is what we actually want to find, I think. What is the uniform distributed charge? Yeah, it's asking us to find this, so we'll solve for it. D over, this is negative by here, by the way. Don't forget that. D squared plus R prime squared. This is a different radius. R prime squared, not R to the 12th. All raised to the 3 over 2. Now, thankfully, we can cancel some stuff. Let's get those K's out of the way. Let's get those D's out of the way. And now, let's solve for Qn. So Qn equals, so on this side we have Q over D plus D squared plus R squared. Let me make my brush a bit smaller. Okay. D squared plus R squared raised to the 3 over 2. That's what we have on that side. We bring a minus sign over, and then we're multiplying by D squared plus R prime squared raised to the 3 over 2. So this is our answer, and the reason we can solve this is because we know the right here, it's asking it in terms of Q, okay, and then we know D. It tells us D. It tells us D. It tells us D. Yeah, D is equal to 1.95 R, and we can get the whole top in terms of R. we can get the whole bottom in terms of r, and it'll end up canceling. In fact, I'm just going to do it just for kicks. So you get minus q times, and then d squared on the top. D squared on the top is actually 1.95 r squared, or 1.95 squared r squared. 1.95 squared is 3.8. 3.8 r squared plus r prime squared. R prime is equal to 3.2 r. So 3.2 squared times r squared. So 10 point that, and then if you add those, you'll get 14. You'll get 14. You'll get 14 r squared raised to the 3 over 2, which is equal to r to the 3 times 14 raised to the 3 over 2, which I'm going to do on my calculator, and I get 52. 52.62, but we'll just do 52. And then on the bottom, you do a similar thing. You get d squared, which d squared is equal to, in terms of r, so we know that. And then r squared is just going to be r squared. So it's going to be 1 times r squared. So 1.95 squared is 3.8, plus 1 is 4.8. So you'll have 4.8 raised to the 3 over 2 multiplied by r cubed. So r cubed, and then 4.8 raised to the 3 over 2 is equal to 10.5. 10.5. These r cubes cancel. And as you can see, 52.62 divided by 10.5, that's equal to minus q times 5.01. So that's basically 5, which is how I got the answer. Anyway, so let's go on to the third one. I don't want to take a super long amount of time. The fourth one is actually probably the easiest. It requires the least amount of... is it electric field? Oh yeah, there is. They sneak in an electric field part. Anyway, so part A. What is the weight of the drop? So let me go to paint. Let me delete all of this. What is the weight? Weight is equal to, on Earth, is equal to your mass times gravity, which is the g constant we know and love, 9.81 meters per second squared. That is what weight is equal to. So let's find mass. So it is a spherical water droplet. It gives us the diameter. So all we gotta do is find the volume, and then we know it's water, so we can multiply by the density to get the mass. So 4/3, actually let me do this on here so it's a little easier. 4, that's not a good 4. 4/3, that's not good either. 4/3 pi radius. So what is the radius? Radius is this divided by 2 squared, because this is the diameter. So it happens to be, what does it happen to be? So 1.9 divided by 2, 0.95. 0.95 times 10 to the minus 6, because it's a nanometer, times 10 minus 6, 10. 4/3 pi r cubed, that is the volume, and this is going to be in meters cubed. Now we can multiply this by 1,000 kg per meters cubed, because this is the density. Oh wow, sorry, my bad. I wasn't on that screen. Anyway, so 4/3 pi radius, because this is the nanometers cubed, meters cubed, that's what it is. And we can multiply by the density of water, which is 1,000 kgs per meter cubed. And then you can do this little canceling thing. You cancel this, and then you get this as the mass in kgs. And then for me, that mass was actually haven't written it down. Actually, I have. Never mind. So 3.59 times 10 to the minus 13 kg is what I got. And then I multiplied by 9.81 meters per second squared. And I got the weight in newtons, which is this. Now, for how many excess electrons does it have? Part B, we have to go back to our lovely friend, the electric field equation. So let's go here. I want to make this a little more legible. So E equals F over q. And so then we can multiply by q, and we don't need to worry too much about the direction of this. It doesn't give us any directions anyway. EQ equals f, and then it gives us q, right? Let me check. No, it gives us e, and we know it's water, and it gives us it gives us oh yeah, it gives us e, it gives us q. No, sorry. It gives us e and gives us f, doesn't give us q. So q is equal to sorry, I'm having a brain blank. EF equals q. Oh, okay, I got it. It gives us E, it gives us F, it doesn't give us Q. So we have to find Q. So 5, uh, 4, 5, 6, let me go back. 4, 5, 6 newtons per coulomb. 4, 6 newtons per coulomb. So let's see. Q equals F over E. So let's put an F on top. F, and we solved for F in the previous equation. Yeah, we solved for F in the previous equation. 3.52 times 10, 3.52 times 10 to the minus 14 newtons. And then this will give us Q in coulombs, which I got 7 in coulombs. 7.72 times 10 to the minus 17. This is what I got. And then we have to divide this by the charge of an electron to find out how many electrons are there. Sorry, I keep forgetting. So what happened is that Q equals F over E, 3.52 times 10 to the minus 14 newtons over E. This is the force, this is the E. This gives us how many, this is Q in coulombs. So we have Q, but we want to find out how many electrons there are. So we take that number, we take 7.72 times 10 to the minus 17 coulombs, divided by 1.6 times 10 to the minus 19 coulombs, which is the charge of one electron, and I got 482.88, which rounds up to 483, which happens to be the answer. Okay, so now number 5. What is the magnitude of an acceleration of an electron in a uniform electric field of that magnitude? So let us go back to here. So we will use the formula again. E equals F over Q, and F equals MA. So F equals MA. Oh yeah, vector hats on all of these on your tests. Otherwise, you'll get bad points. And then it gives us this. It gives us E. So we have 4.5 times 10 to the 6th Newton/Coulomb times Q. And then it gives us, it's an electron, so we know the charge of an electron, times 1.6 times 10 to the minus 19 coulomb, and then coulombs will cancel, equals MA, and we know the mass of an electron too. The mass of an electron is 9.1 times 10 to the minus 31 kg. So then you have this on this side, you have this, then, oh my god, this is like the 8th time I forgot to switch. Apparently this new system of mine, I'm trying to use this thing, is not going to work. So I will not do that. Anyway, E equals F over Q, and F equals MA over Q. E gave us, Q we multiplied by, this is the charge of an electron. This is the mass of an electron. So mass of an electron times A equals this, and then A you can solve for equals this. How long will it take an electron from rest to attain 1/10 the speed of light? Well, that's just kinematics. So V final equals V initial plus AT. V initial says from rest 0. V final 1/10 of the speed of light. Go C over 10. You know, you can look up C. C is equal to. Let me type this. t is equal to 299,724 that meters per second. So c over 10, and this is equal to a times t, and we solved for a in the previous sector portion, uh, times t, and then you got these, you can solve for t, you get this. How far will it travel? Well, that is, so y equals y initial plus v initial times t plus 1/2 a t squared. V initial 0, forget about this. Y initial, start nothing. So y final equals, or how far it travels equals 1/2 a, which we solve for here. 1/2. Why is this not letting? Alright. 1/2 a times t squared, and then t we should have solved for here in the second part, and I got this. So let me just place this here. There, that's good enough. That is how you get that, and then you should get this. So let me try to wrap up with question 6. Oh, this one's the torque. A rigid 1 meter long rod is pivoted around its center. A charge Q1 equals 3 times 10 to the minus 7 coulombs is placed on one end of the rod, and a charge of Q2, a charge of Q2 is equal to minus Q1 is placed distance 9 centimeters directly below it. So, how do we do this problem? Part A. What is the force on Q1 on by Q2? This one is simple. The electrostatic formula. Let me delete this quickly. This is the simple electrostatic formula, which is the force is equal. Wow, what's wrong with this? Equal to K, Q1, Q2 over R squared. Let's go to here. It gives us R. It gives us Q1. It gives us Q2. So, and we know K. K is 8.99 Newton meters per coulomb squared, or coulomb to the minus 2. So we can solve for that. And notice that it will actually be negative. The force should be negative, but I guess it's asking for the magnitude of the force. It depends on your field inertial frame. What is the torque? Torque due to that force. Well, okay, so let me do this here. Torque is equal to force times the length. And we solve for force in part A. And the length, as you can see, is 50 centimeters. So we'll take part A's answer here. And actually, I'll just do it here. Take part A's answer. And by the way, torque is equal to part A's answer times 0.0, actually no, 0.50 meters, and that will give you this answer torque. To counterbalance the attraction of the two cars, we have this on the other side. What is the value of the mass m? Okay, so basically, if there's a fulcrum, the torque on each side is going to be, and it does balance, the torque is going to be equal on both sides. So T1 equals T2. So T1, as we found in the first equation, is 0.05. So right here, 0.05 equals T2, which is equal to the mass. It's equal to the force times the length, and that's equal to for this guy, it's the only force on it is the force of gravity. So mg, because like a is g times its distance, and its distance is in this problem 0.25 meters. 25 meters. We know this. We know this. This is meters. It's kind of confusing. We know this. Solve for this, and then if you do that, you will get this. You'll get it in kilograms. Then you'll have to convert to grams. So for the last one, we now move the block and hang it distance 25 meters from the balance point on the same side keeping Q1 the same and D the same, what should we choose for Q2 to balance this equation? So basically, this block right here is moved over here, so that these things aren't balancing. So there needs to be a change in this charge to change this torque. So basically, if they're on the same side, the sum of the torques is equal to 0 on that side, or on both sides. Oh no, sorry. Uh, torque 1 plus torque 2 is equal to the torque on the other side, which is 0 because there's nothing. So basically, what that means is that torque 1 uh, is torque 1 is equal to minus torque 2, and therefore uh, let's put the minus on this side. So minus torque 1. I'm just gonna write it out for now, so torque 1 F times length. Length is the same. Length is 1/2 meters. So, and then force is K Q1 Q unknown. I'm gonna do Qn. We have to find Qn over distance squared. Distance squared is the same times L, which is 0.5, is equal to Q2, and Q2 is F times A. So it's mg, and we found m in the previous problem, times L. So then we have this, and then we can actually, so we can solve for this guy right here, Qn. So then we get Qn equals minus mg L L2 or L prime. This is L prime. This is 0.25. That was a little confusing. D squared over K Q1 L right here. So this is the L1. This is the point 0.5. Okay. So we have that. If you plug in all the values, you know m from the previous. You know m from part C. You know G. You know this is 0.25 meters. This is 0.5 meters. You know D gives you 0.9 centimeters, 0.09 meters. You know K. You know Q1. You can find Q2, and it happens to be this. Anyway, I hope you learned from this video, and I apologize with all the technical difficulties I'm having. I'm trying to use this, and it's not actually a good idea. Because I heard that my handwriting was bad, but so I apologize for that. Uh, anyway, I hope that you benefited.